All right. So this is not so long ago. It was about 4 years ago. Okay. 2016. Okay. It's your standard end of year paper. We'll have something like this on it. 3 marks. 3 hours, 150 marks. Okay. Obviously, it will start with your section A, which is your question 1, which is all multiple choice. Everything multiple choice, which will cover at least one question of your entire syllabus, at least one from every section. But section B obviously is what we are concerned about because that's where most of our marks come from. 75% of the paper comes from here. Okay. All right, so your first question will always be your grade 11 work. All right, your Newton's laws. All right, it's a standard grade 11 question. All right, besides the 2 different types of friction that you learn. Your question 3, this is your grade 12 question. Okay, VPM, vertical projectile motion. Okay, it's not a big section, but 11 marks can count in your favor, either in passing or failing. Okay, so we'll do that question. We'll also do question 4, which is your momentum and impulse question. Also for around between 10 and 15 marks, right? But usually not more than 15 and usually not less than 10, usually. All right, question 5, this is your work energy theorem question, right? And they include a bit of power in it. Well, they usually do. If they don't, you are lucky. Right, and question 6 obviously is the new section, is the new work that I want to go through, which is Doppler effect. Okay, but we'll work through just up until question 5. Okay. All right. So question 2, like I said, it's our standard Newton's law question. We'll start here, and like I said, it's grade 11, so it has grade 11 weighting. In grade 11, obviously, there was a lot of work and stuff like that that you had to go through. So they just throw in everything from last year into this year with this question here. 18 marks. All right. So a little bit of exam tips today, of course. So question 2, let's go ahead and do it. Okay, so for 2.1, I'm just going to read the same thing that I read already, that when a resultant force acts on an object, the object will continue to accelerate in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. All right, and there you go. Okay. Back to, hold on, let me just close quickly. Back to the question paper. It says calculate the magnitude of the kinetic frictional force acting on the 3 kg block. Okay. Right, so obviously for this one, 2.2, and this is the 2016 NSC paper 1. Skew line, but it'll do. 2.2, so obviously we know that the kinetic frictional force is equal to the coefficient of kinetic friction times the normal force. All right, so if you have a free body diagram, we know the normal force is going upwards, and we know that the gravitational force is going straight downwards, so these are opposite of each other. So we know that the normal force is also equal to the gravitational force because it's just in the opposite direction. I want this value. They gave me this value, and I can obviously convert that into mass times gravity. So I've got 0.15, I think, multiplied by 3 times 9.8. All right, and I'm gonna do this live on my calculator. So I've got 0.15 times 3 times 9.8. I get the value of kinetic frictional force to be equal to 4.41 newtons. All right. Do the people have any questions regarding
No.
Right, did everybody get this?
Yep, I got it.
2.3, which is 3 in French, all right, was draw a label three-body diagram showing all the forces acting on the 1.5 kg block, all right. Jamison, you were arguing with yourself, because that's just what you do, and you were checking if there was tension, correct?
Yep.
So let me go ahead and draw this for you guys. Free body diagram. All right. Boom. All right. I usually start with this one here, FG. Okay. Then I go to the opposite side. Okay, I'm just going to draw it a little shorter. I don't want to touch there. That's FN. Okay. Nowadays they want you to put FN instead of just N and just W for gravity. They want you actually to use FN. So please pay attention to that. It's the normal force FN, gravitational force FG. Please. Otherwise we're going to lose marks for stuff that we don't need to lose marks for. All right. The 25 Newton force was going in this direction. Okay. So we draw it in this direction. Okay. This is the applied force, which was equal to 25 newtons. All right, cool, very cool. Tension in the rope, people. All right, that needs to be included. And then all you need to do is just draw another little line just on top of it, obviously not as large. Okay, and that is your FK. This is not that much big of a value. It's 4.41 newtons. And there's your free body diagram. Any questions? Hello, Dom.
What about and friction? Is that not a thing?
No, yeah, it is. It is. FK, friction. There you go.
Is that oh yeah. Now, if you did the components of the applied force, would it just be like if a y going up and in, if a x going to the right?
The y part, the y component, that's not necessary. You are welcome to include the if x component or if x rather like that. That's perfectly fine. It's not necessary though in this case.
Okay.
Cool. But that was for 5 marks. So obviously we would have 1, 2, 3, and 4 and 5. Of course, a lot of people might have omitted tension and thought they might have gotten a mark for this one. They would have got 4 out of 5. 4 out of 5 is still good, guys. I mean, if you got 4 out of 5, I would say 2 out of 5 is bad, and even 3. But 4 out of 5 is still pretty good. But obviously, we're going for gold here, so tension would have had to be included because there's a rope or there's a string attached between the chair. All right. Okay, that was that. Also 5 marks already. Lovely stuff. 2.4. Calculate the magnitude of the kinetic frictional force acting on the 1.5 kg block. Okay, it's a different story now. Okay, because now the components obviously come into effect. All right, we've got the y component now when it comes to the when it comes to the 1.5 kg block plus the normal force as well. So we cannot omit that. All right, we can't omit that. Okay, so if we're going to find the, I might have to clear some space here. So just get a. All right. So 2.4.1. Okay, so if we're going to have a look here at the 2.4.1, we still use the same formula. If K is equal to mu K times n, times the normal force. Okay. Obviously, looking at the question, okay, what do we saw? What do we saw? What do we see? We had this. Just join this little one part. See, the block is underneath here, but this was the 25 newtons that was being applied. This was at the angle of 30 degrees. Okay, obviously this we have our fx, and obviously here we have our coming down here, we have our y component here. Right. Okay, that's fine. So, and of course we have a normal force also acting on the block as well. Okay, so the vertical components on both of the block is going to consist of Fy and Fn. Okay, so obviously if we're going to look for Fy and this side is 25, we know that opposite over hypotenuse is what? Sine, correct? Right, that's sine, of course. All right, so mu k, we know that value is 0.15 that was given to us. Okay, multiply by Fy component, which is obviously going to give us 25 sine 30. Okay, that'll give us that value, plus the normal force in the opposite direction of gravity, which is just mass times gravity, and that's going to give us 1.5 times 9.8. All right. We pop this baby all into our calculator. All right, therefore, 0.15 multiplied by 25 sine 30 degrees plus 1.5 times 9.8, bracket, brackets, and we get math error. I'm joking. We get 4.08 newtons. 2.4.2 said the tension in the cord connecting the two blocks. Okay. So let's have a look here, 2.4.2. This was a nice question. I always enjoy tension questions. All right. So first things first that we have to do, okay, is find out what is the net forces that are acting on each of the blocks, and then we need to perform a simultaneous equation. All right. So for example, let's take for the 1.5 kg block first. Okay, we have our F net is equal to mass times acceleration. Okay. Okay, then we know that for F net we got for the 1.5 kg block we got F of x. Okay. Plus now tension for this block is obviously going in the same direction as frictional force, which we saw in our free body diagram. Minus T plus friction is also going in the opposite direction, Fk. That's all equal to 1.5 A. Right? Everybody should at least be up to speed there. This component Fx, if you want to find this component, we know that's equal to 25 cos of 30. All right, minus the tension. All right, and that is obviously equal to minus, to be calculate the friction force, minus 4.08 equals 1.5 A. All right, we should all be fine with that one at least. Okay, so if you rearrange for A, okay, let's see, what can we do? So we can obviously solve for 25 cos 30. So 25 cos 30, we punch that in on our calculator. Right, that's equal to 21.65. Just give me 1 second, guys. want to make a note of this quickly. 25, sorry, not 25,65, it's 21,65. Okay, and that's minus 4,08. Right, that gives us 17,57 minus tension. Okay, so once we have that, it will look something like this. Let me just take out the F4s quickly. So you'll have 17,57 minus tension equaling to 1,5 A. All right, so what we want to do, we obviously want to keep that, all right, to the point where we can solve for what you can do is say, therefore tension is equal to, because tension goes on the other side, 17,57 minus 1,5 A. Okay, and you can maybe save that as your equation 1. Then we'll change color, and we'll say, okay, for the 3 kilogram block, let's see what we have here. For the 3 kilogram block, you only got 2 forces acting on it, all right, which you got tension. All right, tension is obviously going that way for the 3 kg block, minus your friction, or plus minus friction. That's all equal to MA, okay? And obviously, F net is equal to mass times acceleration. And then we can maybe go back and a step further to say that's equal to 3A. Okay, we got over here, we got T is equal to 3A minus the force of friction for the 3 kg block, which was 4, 1. All right, so now we've got T is equal to 17,57 equal minus 1.5A, and here we got T is equal to 3A minus 4.4
JP, isn't it
4,41.
positive?
Yes, you are right. Sorry, it's plus. Sorry, my bad. Thanks for that correction. 4,41. So because we got T is equal to both things here, what we could do is we could just equate them to each other. So we could say for the new equation, therefore 17,57 minus 1,5A is equal to 3A plus 4,41. Alternatively, we could have substitute this formula into T in this one. Would have been very much similar. Okay, and I'll show you how. So I just want to I want to organize this. I want to take 17,57. I want to take this 4,41 over to make that minus 4,41 equals 3A plus 1,5A. Okay, calculator, my best friend. Yeah, okay, so answer minus 4.41. Okay, that gives me 13,16. I round it off to 2. And 3 plus 4 plus 1,5, that should be 4.5, 4,5A. And I want to divide by 4.5 on both sides. I should get acceleration to equal 2,92 meters per second squared. Yeah, 2,92. Or if you want to round it up to 3 decimal places, you could say 2,925 because you get 2,9245. So you can say 2,925, round it up to 3 decimal places, but you're not done yet. All right, you still need to calculate the value of tension. Okay, so it would be easier to substitute this value of acceleration straight into our second equation for T is equal to 3A plus 4,41. All right, with that being said, let's go do that now, but I'm just going to clear this half of the board quickly. So 2.4.1. So looking at 2.4.2 still continues. So I'm going to say, well, therefore, t is equal to 3 times 2,925 plus 4,41. And I just plunge that straight into my calculator. Therefore, tension, the value of tension is equal to, let's see, 3 times 2.925 plus 4.41 should give us 13,185, so 13,19 newtons. Okay. If you got 13,17, 13,18, then that is a perfect range. It's still acceptable for the question paper. It's still acceptable. Answer range. It's about, you allowed about 2 to 3 decimal places off, depending on how you rounded off your numericals in this part of the question. All right. Any questions for this section? Would you like me to slow down? Would you like me to work faster? Any questions? Are we all happy?
JP,
Christian?
for the 1,5 block, do you use Fx because it has that 25 newtons?
So you're using the Fx because it's being, the force has been applied at that, force has been applied at that angle. All right? All right, now it's on a horizontal surface, so you need to find out what is the value of this horizontal component, which is Fx here, because you can't use this component or this applied force at this angle without calculating this, because all of your other forces are horizontal. So you're trying to group all the horizontal forces together. Hence, we calculate what is this in terms of this. See what we say? So that's why you calculate the Fx component always only if your applied force is always at an angle. If the applied force is applied at the horizontal direction, then you don't have to do that, of course.
Okay, thank you.
Welcome. If that's the only question, we can turn our focus now to vraag 3, shall we? All right, I hope everybody can see this. Question 3. A ball is dropped from the top of a building 20 meters high. Ignore the effects of air resistance. Okay, 11 marks. Let's go. Now let's start unpacking this question. Obviously, from defining the term free fall, like I said, that's when the object is in motion and the only force that is acting on it is the force of gravity. That's the only force, right? Nothing else. Okay, it's just falling freely to the ground. Okay, we choose the real McCoy question. Okay, calculate the speed at which the ball reaches the ground. Okay, now we need to decide, first of all, just get a new board quickly. Which direction are we taking as positive? All right, now the question that the way that I would do it is I would take downwards as positive because the object is already in free fall and it's already going downwards, so I might as well just take downwards as my positive motion. So for 3.2.2, for example, I'm taking downwards as positive. And the equation of motion that I need to obviously find out, I know my delta y is equal to 20 meters. That's the building. I also know that the acceleration due to gravity is equal to 9.8 meters per second squared. Okay, it was dropped, so it had to be dropped from rest, obviously, and that VI will be equal to 0 meters per second, and VF is equal to our unknown. So the equation of motion that we're going to use here is Vf squared is equal to Vi squared plus 2, G delta Y. Okay? Vf squared is obviously what I'm looking for. Vi 0 squared plus 2 times 9,8 times 20. If, and I do say if upwards was our positive direction, then these two would have to be negative if upwards was our positive direction. Okay. So we have 2 times 9, well, still Vf squared here. We have 2 times 9,8, 2 times 9.8 times 20, and we get 392 as our value here. We need to square root it, obviously. Therefore, the final velocity of this ball when it hits the ground is equal to a crispy value of 19,79. So I'm going to round it up to 19.8 or 90.80 meters per second. All right. And that should have been 3.2.2. Did anybody get that? Everybody get that? Yes, yes, yes. No, maybe, maybe.
Yep.
Yes, in celebration of that.
Yep.
Good. All right. 3.2.3. 3.2.3 is a nice calculation question. This is one of the easier VPM questions because the object is in free fall. Okay. So 3.2.2, or yeah, 3.2. How did I say 3.2.3? This was 3.2.1. That's 3.2.2. All right, is now that we had to calculate the time taken for the ball to reach the ground. That's 3 marks. Okay, so we need to decide on equation of motion here that has time in it. So we've calculated Vf, we know what Vi was, we also know the acceleration due to gravity, and all we're looking for is delta t. So the correct equation would be Vf is equal to Vi plus G delta t, okay? If we used A delta t, it's still correct, by the way, because I'm just using G because it is object is in free fall, it's vertical projectile motion, so yeah, that's what I'm using it for. I sub in 9,80 for my final velocity that I calculated there, equals, well, that's still 0, plus 9,8 delta t. Okay, so all I do is I just divide both sides by 9.8. Okay, obviously, and then therefore delta t is equal to 2,02 seconds. That's time. Everybody get the time correct?
Yep.
Yep.
Well done. Well done, everybody. Good stuff. That's what I want to see. That's what I want to hear. All right. Okay. So again, this is free fall. Sketch a velocity time graph of or for the motion of the ball. No values required. So that means it's just a normal sketch graph of v versus time. Okay. Well, to save getting rid of everything, I can just get rid of this. Okay, obviously we know when an object is in free fall and it's only gravity is acting upon it. Okay, we know we got velocity, that's in meters per second, and we have time, which is obviously in seconds. Okay, we know that in this case, obviously that as the time increases, so does the velocity because it's directly proportional here. So it's just a straight outgoing line like that. And that was your, and that's your graph for 2 marks. Nothing to it. That was it. Okay. I hope everybody got that part. Okay, because object is obviously in free fall. So obviously the longer it falls, obviously the velocity is going to increase. Let us open a new one. Where are we? Yeah. Okay. We might just see how much is 13 minutes, and we got about 25 left. So this might take us all the way through, and I might go through the last question with you guys. Question 4, the graph below shows how the momentum of a car A changes with time just before and just after a head-on collision with car B. Okay, a car A has a mass of 1,500 kilograms, while the mass of car B is 900 kilograms. Car B is traveling at constant velocity of 15 meters per second west before the collision, and they gave you a nice little compass here, so you know where west is. Take east as positive. Okay, now that's an instruction. Take east as positive and consider the system as isolated. What do you understand by the term isolated system as used in physics? Your own answer. And then you got to use the information, use the information of the graph to calculate the following. Okay. So if you look at 4.1, what do you understand by the term isolated system? Now, possibly two answers there that you can give, all right? In an isolated system, so you could either give the first and obvious answer, definitely the answer that I always gave, is in an isolated system, you know, there are no outside interferences, so no outside forces. So that's a system which excludes external forces. Okay, we want to use the word external, right? For 1 mark. It's a system that excludes external forces, right? No outside forces, no air resistance, no nothing. It's just purely just in an isolated, controlled environment. The other option that you can also give is a system where the net force, all right, or resultant force is equal to 0. All right. That's another definition or another answer that you can give for 4.1, but my most go-to answer is where there are no external forces acting on the system. That's for 4.1. Now for 4.2, it says calculate for 4.2.1 the magnitude of the velocity of car A before the collision. Now please, ladies and gentlemen, you're looking at this graph. It's a graph of momentum versus time for car A. All right? It's for car A. All right? So there's nothing really that you have to work out for car A in terms of momentum. Okay? But you have to work out the velocity of car A just before the collision. So looking at the graph, we can see that there's definitely a change in momentum here from where it started out to where it ends. So there's definitely a change. So where you see the change must be where the collision happened. So we can see that definitely before the collision, car A's momentum was at 30,000 kilograms per meters per second. I just read it off the graph. So if I have a look here at my solution, P is equal to mass times velocity. P is my momentum of car A, 30,000, take it off the graph, equals to 1,500, which is the mass of car A times velocity, divide by both sides by 1,500. The velocity of car A before the collision is equal to 20 meters per second, 4.2.2, which asked us to have a look at the velocity of car B just after the collision. All right, so have a look here. They are looking for the velocity of car B after the collision, so VF of B. Okay, we don't know that. We do know its initial velocity. So we know nothing momentum-wise about car B, but we know everything momentum-wise of car A. For example, as you would see here, MA or M1 VI1, that's momentum. All right, that should be this. All right, we found out that was equal to 30,000. right? Initial momentum of car A. Then the change in momentum happened with the car A's momentum went down to 14,000. That's why that's on the VF side. So car A, I've already taken care of. For car B, all right, mass of it was 900 times negative 15 because it's going in a westerly direction. And of course, on the other side here, we have 900 times VB or VFB, all right, because we don't know what is the final velocity of B. If we rearrange our formula, okay, we can obviously get a value here, take that value over and divide them all by 900, okay? Long story short, VFB, or the final velocity of car B after the collision, should be equal to roughly 2.78 meters per second, and in the easterly direction, eastwards. Okay, obviously I skipped out on all the maths because I'm sure you guys can work the maths from here, okay? I'm sure, I trust. Okay, so that's how you would have solved for working out the final velocity of car B. So we can actually go and fill it in here. .78 meters per second. And it's positive, so we don't need to write it out negative. Okay. Last question, 4.2.3, just before we leave, was the magnitude of the net average force that is acting on car A during the collision. This is where knowledge of impulse comes in, all right? This is where knowledge of impulse comes in. Okay. A couple ways we could do this. There are a couple ways we could do it. Let me just check the net average force acting on car A during the collision. All right, so let me just put your attention back here to the graph. Can we see this, boys and girls? See the slope over here? We can see here at the beginning of the slope, the time is what? 20.1 seconds, right? And then at the end of the slope, we got 20.2. What is the difference between them? What's the difference between 20.1 and 20.2? What's the difference? What's the time interval here? Or just 0.1?
Yeah.
All right, perfect. Now that we've established that. Okay, let's go back to our little diagram here. Okay, so I'm just going to clean the board quickly. So 4.2.3. Established that the time interval from 20.2 minus 20.1, we get 0.1 seconds. All right. So in our formula of F net times delta t equals the change in momentum. Basically, we're saying that the impulse is equal to the change in momentum. Obviously, I am concerned with F net. I need to find it. My delta t, I calculated from the graph to be 0.1 seconds. Okay. The change in momentum, I can obviously calculate because on my graph, I see that the momentum of car A was 30,000 newtons. Okay. But within 0.1 seconds change to 14,000. I just read that off the graph. All right. And in fact, it should be the other way around. So I'm going to show that it went from, this was the initial momentum, and it went to 14,000. So when I sub in here, obviously I'm looking for the net force. Net force times 0.1 equals to 14,000 minus 30,000. And it is negative, of course, because we went from 30 to 14. And the change in momentum we know is obviously PF minus PI, right? Final momentum minus initial momentum. All right. Right, if we do that, we're going to divide both sides here by 0.1. That cancels. Divide both sides by 0.1. All right, if you punch that all in our calculator, well, I'm going to get rid of the dots quickly. If net is equal to, we should get negative 160,000 newtons, all right, which is just equal to, stated positively, to be 160,000 newtons. And let's just have a look at the questions before we can add a direction. The net average force acting on car A during the collision. Okay, you are welcome to just leave it at 160,000 newtons, or you can put a direction on them. So we got negative, so it's in the opposite direction of motion. So you can just say in opposite direction. Or in this case, which was west and not east.
Yes. So what happens if I leave it as negative and say negative 160,000 newtons west? Must I change it back to positive?
So you would change it back to positive, and then you'd add this piece on it.
The west.
Okay. This part backs up that part. Okay, and that is question 4 wrapped up. All right, and that's unfortunately all we have time for. We will go through a work energy theorem question next week. I'll do it live, and then we'll move on to Doppler effect, and then we'll stretch the chemistry out as well. All right, so that brings us to the end of today's session.